Hi, I'm Tim. This is my ASE 375 Lab 4 report. Along with me, I have my group mates Holton and Nick Giglio. Yeah, so introduction. So in this lab, our premise is to use the strain gauge to measure pressure in a vessel and in a opening soda can. So when we're measuring pressure, how does that work? So pressure is a physical phenomenon that causes a physical deflection on whatever vessel it's in. That deflection causes some type of physical change in resistance of the strain gauge, and then when the physical resistance changes, it causes a change in voltage given the same input. And because of that change in voltage, we can work backwards and get strain using the strain gauge, and then go backwards with Young's modulus to find the stress and then eventually the pressure. Cool, so how does a strain gauge work? So a strain gauge measures the strain of an object. So strain is the change in length of an object over the original or total length. And the most common type of strain gauge is shown to the side, where it is like a metallic foil, long piece of wire that is sandwiched between two flexible plastic backings and glued to the vessel or the thing you're trying to measure. And then as the object deforms or stretches in a certain direction, it causes a minor change in the resistance of the object, which changes the voltage difference, and that is something we can read. And then we can go backwards and find the resistance, and then the change in resistance, and then the change in length to find the strain. And the formula shown above. Cool. So when we are measuring this change in resistance, it is usually very, very small. So we have to use something called a Wheatstone bridge, which is an electrical circuit that increases the sensitivity and increases the resistance effects on the voltage. So in here below, you can see the configuration of the Wheatstone bridge. So voltage in is something we can control, and along with R1, R3, and R2. Now, the Wheatstone bridge is usually put in location R4, and we usually know its original resistance readings. And what we can measure is V out. So depending on what V out reads, we can go back and solve for the change in R4. And that will, using this equation, the change in R4 over the original resistance reading will get you your strain if we know the gauge factor GF. And then this is good because, again, it increases the sensitivity of the Wheatstone, of the strain gauge by amplifying the differences of the resistance, and that also eliminates noise and reduces the effect of temperature on the strain gauge.
Hey, I'm Holton, and I'm going to talk about the procedure. So we had two parts to the experiment. The first one involved a cylinder, and we had a strain gauge on the cylinder. The cylinder had a pressure gauge. So with the pressure gauge, we could change the pressure that's in the polycarbonate cylinder, and the strain gauge we can measure from the outside, and we can compare the two. We also had this Wheatstone bridge, which was in this full bridge configuration. Here is the setup for our software. So you can see that we started with a DAC assistant, which went to the collector, and we had the statistics and the measurement box, and then we were outputting this waveform graph and the mean indicator and the standard deviation. That was just so we can see what the data is doing as we're taking our measurements. And then for the experiment itself, we have the cylinder, and then we're going to take measurements at 0, 5 psi, so on to 30 psi. We're taking data points at each of those, and then we're going to use these formulas over here to calculate what the pressure is given by the strain gauge. And then so we're going to take that pressure and we're going to compare it to the pressure that would be expected based on our psi that we're measuring with the pressure gauge. We're also going to use the data for the polycarbonate material down here in figure 1, and we're going to use these two equations, 1 and 2, to calculate that pressure given by the strain gauge. For part 2 of the experiment, we're doing a pretty similar thing, except we're going to use a soda can. So we're going to bond a strain gauge to the soda can, just gluing it on there. And then we're going to use the same setup for the software as last time, but for the Wheatstone bridge, we're going to use a quarter bridge configuration, which you can see here, just slightly different than the full bridge. And then so for this one, pretty simple. All we're going to do is take the measurement before the soda can is opened, while there's still a lot of pressure in there. Hook the strain gauge up, make sure everything's going, and then we're going to take the measurement as we're opening the soda can and see how the pressure changes as that soda can is opened. Similar to last one, we're going to use equations 3 and 4, and we're going to use aluminum for the material, as the soda can is made of aluminum.
So here are my results for the lab. So part 1 is the calculated pressure versus the measured pressure. So using the formulas outlined in the procedure, we calculated the pressure using the strain gauge. And we put that on the y-axis and we plotted it against the true pressure reading from the board-in pressure gauge. And as you can see on the graph on the right, you can see that it's roughly linear with a roughly 1-to-1 correlation. And on the bottom here, we take a closer look at the difference of the pressure measurements from the true pressure measurements and calculate it as a percentage of the true pressure measurements. And other than the 10.4%, the rest of the pressure measurements were pretty accurate, around or within 5% of error, which is pretty good. Part 2. So this is the pressure change of a can opening. So this is a dynamic pressure reading. And using the formulas outlined in the procedures, we calculate the pressure change over time of a strain gauge measuring the pressure change of a soda can opening. So you can see that initially the pressure is very high. And as soon as we open it, in like a split second, the pressure drops to pressure atmospheric, which we calibrated to be 0 psi. And this is like the gauge pressure. So 0 psi is relative to the pressure of the atmosphere outside minus the pressure of the inside. So yeah, we define the convention of the gauge pressure. So as the soda is closed, the pressure is higher on the outside than it is in the outside. And you found that the change of pressure is around 41.7 psi.
So here are the results. The results for part 1 of the experiment. We can see here this data was calculated using those equations outlined in the procedure section. That's equation 1 and equation 2, and the material data from figure 1. This is done using the data given in the given data. We had some problems with the Excel sheet for our experimental data. But we can see the expected pressure goes up steady. This is just the pressure that we set our pressure gauge to, so it's at 0, then 5, then 10, and so on up to 30 in a linear relationship. And then this calculated pressure that we found using these equations over here follows it pretty closely here. We can see just a few variations, but barely any variations of note. They're well within the error range. If we move on, we can see that difference between the calculated and the expected pressures charted here. So we see there's never more than a 10% difference, and that's at 5 psi. The reason for that would be just because of the lower number. We have it's off by about 0.5 on our calculated pressure. So of course that's going to show up greater at the lower magnitude of pressure. But besides that one spike at 5, the percent difference is pretty low, which is a good indicator that our calculated data is good and close to the expected pressure data. So here are my results for part 2 of the experiment. This is where we had a soda can and we attached a strain gauge to the soda can so we can measure the pressure before the can is opened and then right after the can is opening, or as we're opening the can. So my results were pretty similar to Tim and Nick's because we only did the experiment once between the three of us, so we had the same results. But you can see the pressure starts real high up here. It starts at 41 psi, and then it's steady, and then right at this point where you have this big spike is where we open the can, and then almost immediately it goes down here and normalizes to an ambient pressure.
Hi, my name is Nicholas Giglio, and this is my video report for Lab 4. So the first step of Lab 4 was to measure strain from a plastic cylinder, a polycarbonate cylinder. To do this, we had a strain gauge attached on the surface. We had a pressure gauge that was mounted on the top, and the lab had us pressurize this container and get strain gauge readings from it, as well as record pressure measurements every 5 psi. We then converted the strain gauge voltage readings into a gauge strain, and we converted the pressure readings from the pressure gauge on top of the vessel into hoop strain using a hoop strain model. Gauge strain was calculated using a gauge model that converted the voltage read into a strain reading. We can see here that both readings start out similarly initially and then start diverging. I think there are a couple of big reasons for this happening. Number one, noise. I think noise in the system can definitely alter readings, especially when it comes to, well, this only applies to the gauge strain, really. So that can be one of the factors affecting the differences in measurements. I think that the second big factor is the visual reading of pressure. I think that visually reading pressure from a gauge is not very accurate and can introduce a lot of discrepancies into your calculations. I think a better way of achieving that would have been to have a pressure transducer along the system to get us lab view readings and give us a better accuracy in our calculations, specifically with hoop strain. I think that would have definitely closed the gap, especially at the higher PSI levels, and solved a lot of those issues. This next slide here shows the percent error in both calculations. We also calculated pressure from the strain gauge voltage readings and compared that to measured pressure from the pressure gauge. That's where the pressure error comes from. The strain error comes from the hoop model theory, the hoop strain theory strain, and the measured strain gauge strain. That's where the strain error comes from. And I thought it was very interesting that both errors kind of follow the same path, even though they're coming from different calculations. We can see also that the error decreases as pressures increase, so it has an opposite relation to the strain and pressure readings. The last part of the experiment had us measure pressure in a Coke can. To achieve this, we glued a strain gauge on a Coke can, let it cure, and then we hit record on LabVIEW and open the Coke can. And as we can see here, the data is, I think, pretty spot on. We can see that initially the coke can starts at about 41 psi, and then instantaneously drops down to ambient pressure, which is pretty cool to actually get to visualize that. I think there are some sources of error here as well, specifically coming from noise in the strain gauge, and also from, as we can see here, the pressure increases right before we open it, probably from gripping the can. I think that could have been solved with multiple iterations of the experiment. However, we can't be wasting coke like that, and so we only get to do it once. I think the conclusion here is that strain gauges are very handy, very accurate, and I trust them. I would say I trust them more than proof strain or than model strain, specifically when using high accuracy systems like National Instruments. Their stuff is really, really quality stuff, and I think it keeps a lot of noise from being introduced into our calculations. And so I do trust the gauge strain a little bit more than I do the calculated models. I think a big improvement for the lab would have been to add a pressure transducer and have pressure measurements along with strain measurement from a strain gauge, and to be able to compare those two. I think that would have been more accurate than having a gauge that is visually read by the students, and that would definitely decrease the gap we see here in this graph. And that is all I have for this report. Thank you so much.